So it's the last lecture, and I'm going to change completely the topic, but still with production functions. We are going to talk about increasing quasi-concave Coradian functions. And this is based on a paper I wrote with Alex Rubinov and Siegfried Scheibel in the journal Mathematical Methods of Operations Research 2005, volume 61, pages 261 to 280. Again, if I have an electronic copy, so I can send it to whoever is interested. I told you about Alex Rubinov. Siegfried Scheibel was also a very important mathematician in our area. The book I somehow followed, Generalized Concavity. He was one of the co-authors. He was a German mathematician working in the University of California at Riverside. So German in the US, but with a Canadian passport, because he had spent some time in Canada before moving to California. He passed away too. So unfortunately, I am the only survivor of these three authors. By unfortunately, I mean not survivor, but only. Okay? Okay. Then, and this paper came from an idea of Siegfried, who was visiting for a short time Barcelona at the same time of Alex Rubinov was also visiting, and he said, look, economists use the property of decreasing returns to scale, which we consider implicitly to be equivalent to concavity, but this is not true. So let us see what happens in general with quasi-concave production functions, which are not necessarily concave, but they satisfy this property of, as economists say, diminishing returns to scale. Then in mathematics, we call these functions Coradian. This is going to be a production function. We are going to interpret it as a production function, but for convenience, I allow it to take any extended real valued value. So we say that f is Coradian I'm not going to go into the justification of this word by geometric arguments, but it's related to Coradianness of level sets. And what is Coradianness of a set? First, I should say what is radianness. So a set is radian when it is star-shaped with respect to the origin. So the origin is in the set, and for every other point in the set, the segment joining it with the origin is contained in the set. So this is star-shapedness with respect to the origin, and it's called radianness. So coradianness is being the complement of a radian set. So if you have a point in the set, and if you draw the line joining it to the origin, in the half line emanating from that point in the opposite direction to the origin, all that half line belongs to the set. This is Coradian. So this is related to this geometric property. You can check the equivalence. I think it's with the upper level set. You can check, it's easy. But the property is that f of beta x is less than or equal to beta f of x for every x in R plus n and for every beta greater than or equal to 1. So, interpreting f as a production function, this means if you multiply your input vector with beta, so you increase, then the output you produce increases less than proportionally. Okay? You double your input, but the output is less than twice the output you produced before doubling. And this is what economists call the property of decreasing returns to scale. Decreasing returns to scale. Graphically, this means that these slopes are decreasing. I mean, if this is x, and this is higher, so this is beta x, then this would be, this is the graph of f, this would be beta f of x, and this is f of beta x. So this means that this slope is decreasing. The slope of the segment joining a point in the graph with the origin. This is for a one variable function. For a several variable functions, it's the same along rays. It's a property along rays. I only care what happens in the ray determined by x. Okay? That's the property. Equivalently, f of alpha x is greater than or equal to alpha f of x for every x and for every alpha between 0 and 1. I mean, they are equivalent by setting alpha equal 1 over beta or beta equal 1 over alpha. Okay? As you see here, I mean, concave functions have this property. Concave functions, which are reasonable of production functions, so that out of 0 you produce 0. Because then f1 minus lambda times 0 plus lambda x is less than or equal to 1 minus lambda f of 0 plus lambda f of x for lambda between 0 and 1, and this gives f of lambda x less than or equal to lambda f of x, which is this property here. Is this property here? Oh, wait a second. No, I'm using concavity, and I wrote the convexity inequality. Okay, no, it is correct. But there are functions which are quasi-concave, continuous, whatever you want, non-concave, but still they satisfy the Coradian property or the decreasing returns to scale property. Consider a function which starts concave, starting with 0, and here it continues convex with this line as an asymptote. Then these slopes will still be decreasing after the inflection point. So even though the function is not concave, it has the Coradianness property. Okay, so the economists should not identify concavity with the decreasing returns to scale property. So we consider this kind of functions. They enjoy nice properties. Well, in fact, it's better to consider just non-negative valued functions, but to allow the value plus infinity. And this is a nice class of functions. The sum of two Coradian functions is Coradian, as one can easily check. The product of a Coradian function with a positive number is Coradian. The limit of a sequence of Coradian functions is Coradian. The infimum of a collection of Coradian functions is Coradian, and the supremum of a collection of Coradian functions is Coradian. So the family of Coradian functions has a very rich structure. Let us first see a characterization of Coradianness in general for an arbitrary function, and then we will see another characterization of Coradianness for quasi-concave functions. Okay? So the first characterization is for differentiable functions. So you have the following proposition. If f finite valued is differentiable, finite valued and with non-negative values, as production functions are, is differentiable on R plus n and continues on R plus n, then F is Coradian if and only if f of x is greater than or equal to x transpose f of x for every x, gradient of for every x in the positive orthant. First order characterization of corradianness. Very easy to obtain. In fact, I will prove that this function, under this assumption that this function is corradian on the positive orthant, and by continuity, the results extends to the whole non-negative orthant. Okay? And the proof is very short. Is consider given x consider the function phi sub x no n defined by phi x of t equal to f of tx divided by t. It immediately follows from the definition that this function is non-increasing. Okay? So look, right here, beta. F of beta x divided by beta, which is the value of that function at beta, is less than or equal to the value at 1, and beta is greater. Okay, I'm comparing beta with 1, but I could compare beta with any other thing by very elementary operations. So the point is that f is corradian if and only if phi x is non-increasing for every x in the positive orthant. And I insist that I work only on the positive orthant because I can move to the whole orthant by continuity. And now let's compute the derivative of phi x. That's it. So phi x prime of t, this is a quotient, so denominator times the derivative of the numerator minus f of tx times the derivative of the denominator, which is 1, and this is divided by t squared. Is this computation correct? Seems so. Is this? Okay. I'm a little bit surprised. I should obtain, so denominator, and then the derivative of this is this minus this divided by t squared. It seems that I get well, if f is corradian, There must be some very silly mistake with the derivative, which I cannot identify. Is the derivative correct? Denominator times the derivative of the numerator. Sorry? But the derivative is well computed? Hmm? Hmm. So it's not correct? So I'm thinking, only one thing? Ah, yes, because the derivative of this is x, not tx. Sorry, this was the mistake. Thank you. I knew that there would be some mistake. Okay. And now there is no problem. Thank you very much. Then that's it, no? Because if f is coradian, associate this t with x, then the if f is coradian, this is not increasing, then phi prime x of 1 in particular is greater than or equal to 0. This happens for every t. The derivative is non-negative. So setting t equal 1 here, we get this inequality. Okay? We get exactly this inequality. In the opposite direction, if this inequality holds for every x, it not only holds for x, but for tx. And this means that this expression is non-negative. That is to say, phi x is non-decreasing, and we know this to be equivalent to f being coradian. Okay? So this is not very surprising. Have you seen a similar relation somewhere? If instead of oh yes, but I think it's here is non-decreasing. So I wrote it correctly, but non-increasing means the derivative is, thank you very much, the derivative is less than or equal to 0. Now everything is correct. But now the question. So if instead of writing here greater than or equal to, I write equality, this is a characterization of what? This is Euler's characterization of homogeneous functions. Okay? This is not surprising because that characterization comes from the fact that this auxiliary function is constant, is equal to f of x, if we have linear homogeneity. So in that case, inequality becomes equality. So this is quite similar. Okay, so it was very simple, although I had some little difficulties with the proof. But next it comes the interesting theorem. Which is the last theorem I am going to prove in this course, but not the last theorem I'm going to state. Then, the theorem says if f a non-negative real-valued function on the non-negative orthan is a nice production function, so it is quasi-concave, non-decreasing, upper semi-continuous. These are the nice properties for a quasi-concave, for a production function, right? So now, on top of these properties, I add coradianness. Is all these things in coradian? If and only if. So what I'm going to present now is a generalized concavity property. So I'm going to prove that these functions are the pointwise infimum of a collection of elementary functions. So stated in this way, there is a subset of R plus n cross R plus such that f of x is equal to the infimum over x star k in S of maximum of x star xk for every x. So look at the function with this structure. The maximum between a linear function with non-negative slope, because x star is in R plus n, and a non-negative constant. Okay, it's a constant. So in one variable, you have a function with non-negative slope, you have a non-negative constant, and you take the max between them. It is it has all these properties, it's immediate, but also look at the slopes. Here the slope of the segment joining a point in the graph with the origin is decreasing, and it continues being decreasing from this point on because it becomes constant. Okay? But look in general. This function, every individual function, so we are saying that f can be expressed as the pointwise infimum of a collection of functions of this type. But how are these functions? Each individual function of this type is quasi-concave because look at the upper level sets. If the level is smaller than k, then the upper level set is the whole space because the maximum is at least k, which is higher than the level. But if the level is higher than k, then the maximum being above that level means this is above that level. And this defines a half space, a closed half space. So again, a closed convex set. So this is quasi-concave. Clearly non-decreasing, because this is non-decreasing because X star is non-negative. Taking the maximum with a constant does not destroy non-decreasingness. For upper semi-continuity, you can use the same argument as to prove quasi-concavity. The upper level sets are either the whole space which is closed or a closed half space which is closed. So it's upper semi-continuous. And coradian. What happens if I multiply x with beta? Beta being greater than or equal to 1. Okay? Then I can write that this is beta times the maximum between x star x and k divided by beta. Okay? And k divided by beta is less than or equal to k, because beta is greater than or equal to 1. So I have decreased the k, so means I have obtained, of course this depends increasingly on k. So I have obtained something smaller here. So this is less than beta times the maximum between x star x and k. Do you agree? I mean, beta, and when k over beta is replaced with k, I am increasing. So the value of this particular function, how you want to call it, g, at beta x is less than or equal to beta times the same function at k, at x. And this is the Coradianness property. Is this clear? So, I have found, I am considering a class of what we can say elementary functions having all these properties. And I'm going to prove that by taking pointwise infimum, I generate the class of all functions with these properties. Then, of course, of the two implications, the one which is an easy exercise is from right to left, because For which S? First, I should define, no, even if there is just some S. Okay? So suppose F satisfies these conditions for some S. Then, what can I say of one function of this type? No, the implication from right to left, we already know. I mean, the immediateness comes from the fact that the properties of being quasi-concave, non-decreasing, upper semi-continuous, and Coradian are stable under the infimum operation. So infimum of quasi-concave is quasi-concave. Infimum of non-decreasing is etc. And then these functions, we already proved that individually each one has all those properties. So the infimum of this collection of functions has all those properties. And the infimum, we are assuming it's f of x. So it's immediate that if f has such a representation, then it must be quasi-concave, non-decreasing, upper semi-continuous, and Coradian. Now, we have to work much more for the converse, because we have to produce S. But S is very easy to produce. So the difficulty will be in proving that the natural S works. So S will be the set of all parameters here for which this is a majorand. So I am considering the set of all majorands of F. So if you want to be very formal, define S as the set of x star k in R plus n cross R plus, such that the corresponding function is a majorand of f of x. So this is a way of saying that I am considering all majorands of this particular type of f. And I am going to prove that f is the infimum of all of its majorands of this type. Okay? And then what is immediate is this inequality. Because I'm taking majorands. So each individual function is greater than or equal to f of x. So the infimum is greater than or equal to f of x. So the hard work would be to prove that the opposite inequality holds true. So to prove this inequality, I consider will proceed as I have done already many times. I consider K to be any number greater than f of x then I will prove that the right-hand side is smaller than k. Since k is arbitrary, but greater than f of x, then the right-hand side will be smaller than f of x. Okay, we have done it 1,000,000 times. So I consider any k greater than f of x. And what does it mean? You are used to this kind of reasoning that u does not belong to the corresponding upper level set. And now it's already routine for you that when you have a point not belonging to a closed convex set, and this is indeed convex and closed because our function is quasi-concave and upper semi-continuous, then you separate. So you say there exists a vector y star in Rn and a number t such that y star y is greater than or equal to t and is greater than y star x for every y in the upper level set. So there is a half space containing the upper level set, and the point which is not in the upper level set is not in the half space. The hyperplane separates. Now, as we have already done once, I can move t a little bit to the right. I mean, make it a little bit smaller, but still greater than y star x, and then because I have decreased t, these inequalities are satisfied strictly. So nothing happens if I can write here y star. Now, and notice that this is non-negative, because everything there, no, don't notice that it is non-negative yet. And because we don't know anything about y star, but we will know very soon. So y star may have negative components in principle, but two cases. Suppose that this upper level set is empty. Then there is no condition on this side because there is no y in the upper level set. So the only condition we are requesting is this inequality. So exists just one vector. So you are free to choose whatever y star you like, compute y star x, and take t a higher number. And that's it. So y star is the vector you like. And then you like it non-negative. If this is empty. And if this is non-empty, you can pick a point here, and using this point, use a classical argument saying that you can move in a non-negative direction without leaving the upper level set because f is non-decreasing, and this implies that y star is non-negative. So either it must be non-negative if this is non-empty, or you can choose it non-negative if this is empty. In any case, do you agree that I can consider that y star is non-negative? In fact, it must be non-negative unless this level set is empty. And now I can say that this is non-negative, so T is strictly positive. And then, similarly to what we did once, I can normalize by dividing by T. Okay? So I take x star y equals, let me change a little bit the notation. Let's call this k bar, because I will consider general k later on. Okay? So I define now x star bar by k bar divided by t y star. F of x is non-negative, so k bar is strictly positive, t is strictly positive, y star is non-negative, so our vector is non-negative. Then suppose, let y be in R plus n. I'm sure you accept that either f of y is less than or equal to k bar, or f of y is strictly greater than k bar. No doubt. So assume that the second case holds. So if f of y is strictly later than k bar, then well, y is in this upper level set, so we have y star y strictly greater than t, which means that t over y star y, which is in R plus n, satisfies the equality y star inner product this vector is equal to t. Is equal to t. So it does not satisfy this strict inequality, so it cannot be in this upper level set. So this point does not belong to this upper level set, that is to say, f of this point is less than or equal to k. Is strictly less than k bar. This is k bar, this is k bar. Being in the upper level set means the value greater than or equal to k bar, and not being there then means strictly less. But it is time to apply. So for the time being, we only used quasi-concavity and upper semi-continuity to separate. And well, we also use non-decreasingness to say that y star is non-negative, but we have not used the Coradian property so far. So it's time to do it. So what do you know about this coefficient? T divided by y star y is less than 1. Okay, then this should be greater than or equal to T over y star y times f of y. I have to erase there. So what I have obtained is that f of y is less than k bar divided by t y star y, but k bar t times y star is what we called x star bar. What is the conclusion? That f of y is less than or equal to what? It is either less than or equal to k bar or greater than k bar. And if it is greater than k bar, it is less than this number. So this is less than or equal to the maximum between x star bar, y, and k bar. I repeat, saying that something is less than or equal to the maximum between two numbers means that it is less than or equal to one of the two. And this one is either less than or equal to k bar or not. If not, if it is greater than k bar, then we have proved that it is smaller than the first. So it is less than or equal to the maximum of the two. And this has been done for every y. So what's the conclusion? That we have got a majorant of the type we like for our function. Or with the notation we have introduced, that the pair x star bar, k bar belongs to S, because S is the set of parameters corresponding to majorants, elementary majorants of our functions. And now we are almost done, because what is the value that this particular majorant takes at y equal x? So what can you say about the max of x star x, x star bar x, and k bar? Use the definition of x star bar. K bar over T. Y star. So y star x, comma, K bar. K bar is positive. So this is K bar times the max between y star x divided by t and 1. And y star x is smaller than t. So this ratio is smaller than 1. So the maximum of the two is 1. So this is K bar. So the proof is finished. I mean, if you want full details, I have to write one extra line. So the extra line is the right hand side infimum x star k s of the max between x star x and k is less than or equal to one particular value of x star in S, which I will take x star bar k bar, and we know this to be equal to k bar. So the right-hand side of this equality is less than or equal to any number strictly greater than f of x. So this right-hand side is less than or equal to f of x. And hence we have equality. That's the end of all the proofs. I have made many in this course. But as I said, not the last theorem. I will tell you something very interesting and very surprising, which when we found it. It probably deserves some further analysis, but nobody was interested. So suppose we have a production function that for convenience I'm going to assume that it may take the value plus infinity. It may take, it's not obliged to take, but it may take. Then I think I have not copied the right word in the paper. I think that what we call the secondary production function, the term is not very beautiful. Or the secondary dual function. I don't remember. I wrote here dual, but maybe I miscopied. Okay, let's say the secondary function, and then we do not commit ourselves with any of f, is the following function, which in the paper we denoted f hash. Very strange function, but it appeared naturally when dealing with all these things. secondary production function. But dual would also make sense. From R plus union plus infinity this is defined as a function of prices as, look at this very strange definition. Supremum of f of x such that px is less than f of x. It appeared naturally from mathematical considerations. But what's the meaning? Given a price vector, well, first of all, a production function is something producing a given amount of output. But here I am comparing money with output. So I assume that the output is money. I mean, the output is not money, but then I will sell the output and I will obtain money. So f of x is directly the money obtained by selling the output. The price of the output is given. Okay? Then, so I am a producer, and if I have in my factory a certain amount of inputs, I may choose between using them to produce, or if I am lazy and don't want to produce, go to the market and sell them. Okay? Somebody else will do whatever. Then I get this money. If it's better for me to produce rather than selling, then that's okay, and then I consider this possibility. And then among all these input vectors for which producing is worth, I am looking for the one that the amount of money I can get. Problem, among other things, because this is a strict inequality. So this means if I have equality here, but then as I said, I am lazy, so I decide to sell, so that f of x would not enter in this maximization problem, optimization problem, but it appeared. Why? Because it is related to this Coradianness property. So the last thing is at the same of these secondary production functions and a duality result between production functions. So it says, let, and the proof is not short, previous result. but it's not a direct consequence of the previous result. The previous immediate corollary. So let capital phi from R plus n union plus infinity, then it is a secondary product a production function such that the associated capital phi, if and only if quasi-convex, non-increasing, and lower semi-continuous. So in this case, we know that there exists F. But as usual, F is not unique. But you can take F to be regular. So in this case, F can be taken quasi-concave, non-increasing, upper semi-continuous, the typical regularity assumptions on a production function, and Coradian. Under these conditions, these regularity conditions, F is unique. So there are in general infinitely many F producing the same F dash, F hash, but only one which is regular and Coradian. Namely, F is the largest function, let's say the largest G, such that G hash is phi. And now you will see the relation with the previous result. This very special F, how can it be obtained from capital phi? F of x is equal to the infimum over P in R plus n of the maximum between Px and capital phi of P. Now you see the minorans, you see the expression. So you see the relation with the previous result. So now is the real end of the course. What remains is to thank all of you very much for your patience, your perseverance to come here every day, for your participation, helping me to correct the many mistakes I made in computations, etc. And well, I hope it was, I know it was boring, but hope not too boring. And then that you have learned several things, not just the theorems, but that the beauty of convex analysis goes well beyond convex analysis, extends to economic theory. There are many other beautiful topics in mathematical economics. I don't know what happens nowadays in mathematics, in schools of mathematics, because since 1990 I am working in a school of economics, and I don't know what is going on now here in India. But in my old times in mathematics, students only learn applications to physics. And I hope now you agree that there are very beautiful applications in economics too. Another fantastic field of applications is game theory. In macroeconomics, which doesn't deal with individual agents but with the aggregations of such individual agents, optimal control plays an essential role. I mean, almost every branch of mathematics, not to say probability theory, stochastic analysis. In finance, stochastic differential equations are the tool. Every field of mathematics is applied in economic theory. Andreu Mascolell wrote a book, not the one I mentioned about microeconomic theory, but with the title General Equilibrium, a Differentiable Approach, in which there is a lot of differential topology there. So really everything. So I hope from now on you will think that economics, economic theory, may be worth looking at for your future research. So again, thank you very, very much for your kind attention all the time.
Round of applause to Professor Juan Enrique for this marathon course. And in spite of having many health issues, he kept on giving his lectures and preparing and interacting with all of us. And indeed, in this lecture, not only we learned many new things and related to optimization and its applications, but also we learned how to prove new results. Somehow we know that how to connect different results and how we can prove this. And of course, the motivation that he gave all of us, it will be with us throughout our careers. And from now onwards, I think, in one of his lectures, he told that he was attending a lecture of Seibel, and then he was not able to understand a few things, and then he told that it is the time to understand it. So it's about if you are ready to understand anything, if you give your 200%, then you will be able to understand many concepts of mathematics. It's all about giving time to it. So again, thank you, Professor Juan Enrique, for accepting our request to give this course in India, and for of course 10 days. It's a long duration, but yeah, we are really grateful to you.
I'm very grateful to you for the invitation. I have enjoyed a lot. Let me make probably a rectification to what you said about Seibel. You probably mean an anecdote I told you once, that it was in 1999 at a generalized convexity conference in Samos. I presented a paper which I considered it to be very difficult to present because it was with ugly formulas, etc. But I made a big effort to make a clear presentation, and I thought I succeeded. So I went to Siegfried to ask him, what do you think? I was expecting to be praised by him. You did great. But he was not very enthusiastic. He said, no, it was okay, but look, I had a colleague or a professor who said, every presentation should consist of 3 parts. This is what you meant? The first part should be understood by everybody, even those who don't make any effort to understand. Second part, only for those who make an effort. And third part, by nobody, even those who make an effort. But, okay, I understand his point, because if they understand everything you say, they may think that it is trivial. They don't appreciate your effort to make things clear. They say, okay, he's telling trivial things. But, okay, I prefer the risk of being considered to be doing trivial things. It may be true, after all, than not being understood. So if you don't understand me, it's not because I try not to be understood, because I'm not enough to express myself more clearly. Because what do we do mathematics? There are many possible motivations, but my motivation is to enjoy. And the best enjoyment is to communicate. So I want to communicate. So for this reason, I have always sometimes not been very careful, and I had some bad experiences when sharing my work before being published. I have one bad experience on one occasion, but okay, then I don't want to keep it for myself. If I don't communicate, I don't enjoy it. Okay, that was a comment about what Scheibel said. Okay.
But we all witness the efforts you have given to make it understood, and I think all of us enjoyed a lot.
Thank you.
And that is the essence of the course.
Thank you, Vivek. Technique?
The things you analyze, all these things.
You are talking in general.
Yes.
Technique, no. I mean, you work, and after some time, depends on how smart you are. It may be in 1 week, or it may be in 20 years. In my case, it's 50 years, I don't know. Then you get some insight, and then you know. Yeah. So there is no recipe. It cannot be done. For the time being, AI is unable to do what we do. Okay, but I'm afraid in not a very long distant time, it will be able to do it. Then we are all jobless. We have to, well, I am already jobless.